okay? So here's the constraints of the problem. The tennis court, not very smartly, I don't know who would build a tennis court up against a house, but we got a tennis court built right up against the house. So probably if you have a fenced in backyard, this is the way it works. Here's your house and here's the fence. So that one side doesn't require any fencing because it's your house, right? So we want to fence in the biggest area that we can. What is the area of the largest court that he can enclose? Now, our restriction is, this is the fence right here, all this is fence, but the restriction is we have 300 meters of fencing. Okay? So let's see. Any thoughts on how we want to maximize area? So we're going to need a formula for area, an equation for area. So any thoughts on how we might start this problem? Well, something has to be x, right? I mean, something's unknown. So what do you want to call x? Well, now I've got 300 meters of fencing. I know that. I know I've got 300 meters. It tells me in the problem. Well, I'm going to use it all. I'm going to use every foot of that fencing.
The area of the court?
The area of the court is actually going to be y. Because the area is going to depend on what? Okay, I want you to think about this for a second. You got 300 meters of fencing. So let's suppose you build you say I'm going to put 10 feet here, 10 feet here, and then that would leave 280 feet here, right? Here's your house. What's the area of that court? 2,800. All right, well, what if you built one like this? What if you made this 50 and this 50 and this was 200? What's that area?
1,000.
I think it's more than 1,000. 10,000. That area is 10,000. So I made it bigger, right, by changing the dimensions. Your job is to make it as big as possible. So what's x? Okay, x, now two of these sides are going to match, right? It's a rectangle. And then what would the other side be? 300 minus 2x. Because you're taking 300 and pulling off x up here and x up here, so that would be 300 minus 2x. So what would your equation for your area look like? X times 300 minus 2x? Or if you distributed that, multiplied it out, 300x minus 2x squared?
Why do you have an area equals and then a y equals?
Area is y. Now, that equation's a little backwards, but what is that? What shape is that? That's a parabola opening down. And what are we trying to do? Area of the largest chord, aren't we maximizing? So when we talk about a parabola opening down, the maximum is just the vertex. So we're going to find the vertex of this, right? And how are we going to do that?
Find the equation.
Negative b, watch it, it's backwards. So negative b over 2a would be 75. So according to our work, this is 75. What would this be?
150.
150. So what would be the maximum area then? The maximum area would be what?
150 times 75.
150 times 75, which is 11,250 square feet. So it says, what is the area of the largest court? It would be 11,250. If it said, what are the dimensions of the largest court? You would say 75 by 150. Easy enough? Turn the page over. Look at number 5. I'm just on the back of the quiz I just looked at. I'm on the back, and I'm looking at problem number 5. Have we ever seen anything like this before? What's going on there?
The same as the before.
The same as the rent problem and the Coke problem that you just did right before lunch, right? So what are we trying to do? We want to maximize our income. So what's our income right now? Before you make any changes, what's your income? 2 times 100? Right? This is the price, and this is the number you sell. So right now, he's making $200. But he's going to change that. He's going to raise the price of his tennis balls. Every increase in price, he's going to lose 2 customers. So for every $1 increase, he loses 2 customers. Braden, what are you doing? One good test does not make us a Precal master. All right, our income. How are you going to express the income? You are going to start adding dollar increases. So what does that look like? You're adding increments of $1. So what's that price going to look like?
2 plus 1.
2 plus, I'll go ahead and put 1x, but you don't need the 1 obviously, but it's $1 per x. They're $1 increments. And how many are you selling then? 100 minus 2x. You're losing 2 each time. So if we FOIL out, we get 200. So we have negative 2x squared, 96x, and 200 if I multiplied right. Now, what am I trying to do? Read the question. Maximize. This is a parabola opening down. Maximum would mean vertex. So x equals negative b over 2a. Is that 24?
Yeah.
Yep. All right. $24, 24 tennis balls, 24 what? Price increases. So I'm going to increase my price 24 times. So what's the question? What price should he charge? $26. The original cost was $2, and we're adding $24 to that. I know, it makes no sense, I made it up. But I knew it was going to be a big number when I read the problem, because the original price is only $2. We're adding another, basically adding 50% onto that, adding a $1 increment, and only losing 2 people. You'd want to add on a whole bunch if you're only losing 2 people each time. So it just doesn't make any sense. But anyway, we did the math. All right, and then number 6. The length of a picture is 5 more than the width. The area of the picture is 66. Find the dimensions of the picture. Now, read it, pay attention to it. Does it say anything about a maximum or a minimum? No. You are not concerned with vertex, people. Vertex is a minimum or a maximum. We are not doing vertex. We're still going to write an equation. What's that equation going to look like? Here's the picture. And it says the length is 5 feet more than the width. What's that going to look like? So x will be the width and x plus 5 will be the length. The area of the picture is 66. How do I do area? Length times width is 66. Right? So x squared plus 5x minus 66 is 0. It's a quadratic equation. I'm not finding a vertex. I'm solving this equation. What is going to work? Does that by any chance factor?
Yes.
X plus 11, x minus 6. Remember, as always, if you don't see how it factors or you don't want to factor it, what else could you do? Quadratic formula. Yep. So don't feel like you have to factor. So x either equals negative 11, we're going to cross that one out, right? Can x be negative 11? No. Called an extraneous root. Or x equals 6. If x equals 6, x plus 5 equals 11. So what are the dimensions of the picture? 6 by 11. This is a rectangle problem. And the tennis court one we did was a rectangle problem. But we handled them very differently, didn't we? Because the tennis court one asked me for a maximum. So I had to do the whole vertex thing. This one said just solve it. It's an equation, solve it. Is that okay? All right. Now, you'll get to practice some various kinds of problems in your homework. Now I want you to turn to 2.2. These involve what are called power functions. Now, this is, of all the sections in our textbook, this is probably the section that I think we need, is probably the shortest amount of time spent on it. A couple of key ideas though, and I'd like you to look for these key ideas on page 197, page 197, at problems 37 to 42. First of all, power functions are exactly what the word would suggest. Power functions are things like x squared, square root of x, 1 over x. Now, why are these power functions? And this is not a power function. And this is not a power function. These are not power functions. These are. Now, in order to answer that question, you do need to remember something about radicals. This is to the 1/2 power. Radicals mean raised to the 1/2 power. 1 over x means raised to the negative power. right? So to be a power function, why is that iPad back up again? Okay. To be a power function, you have to have x being raised to a power. And depending on the size of the power, that will determine the curve. Okay? Now, there are three that you are real familiar with already. Three power functions that are real easy. There's that one, so there's y equals x to the first, y equals x to the second, and y equals x to the third. Those are very different shapes. I'm not going to dispute that. But they all have something in common. The bigger x gets, think about it, when you draw this, what happens in quadrant 1 when you draw this? It goes up. What happens here when you draw it? It goes up even faster. And what happens here when you draw it? It goes up even faster. So when you're raising to powers bigger than 1, your curve is shooting up faster than, depending on how big the number is. The bigger the number, the faster it goes up, if the power is bigger than 1. So I'd like you to look at the pictures that you have there in exercises 37 to 42. I see equation C, it's in red in my book. Are they colored in yours?
Yes.
And equation B are both exhibiting this kind of behavior. So I'm going to look through my list of equations and find exponents that are bigger than 1. So let's see. I'm looking for B and C now. Well, this is a trick question, because I don't even see a B and C equation in there. Now, 37, why am I not picking 37? What's different about 37? It's got a negative out in front. What's that going to do? It's going to have this shape, but it's not going to be going up, it's going to be going down. So is there something that looks like that? That would go with equation 30, or problem number 37. That would go with equation G. Its power is bigger than 1, so it has this shape, but it's going down. What about F? Do I have anything for F, any equations for F? Well, what about 40? 40 has a power bigger than 1, and it's negative. It's another G. 37 and 40 are both G's. Here's why. I feel like I'm not explaining this very well. Here's why. When the power is bigger than 1, you have a power function, so x is being raised to a power. When the power is bigger than 1, you're shooting up. You have this kind of a shape. Now, this is a line, so this would be x to the first. Anything that's a straight line is going to be x to the first. If it's going down, then it's negative x to the first, because all the ones down here are negative whatevers. So if you have a negative x to the 7/5, that's going to have this shape. Anything bigger than 1, if it has a positive coefficient, it's going to go like this. If it has a negative coefficient, it's going to go like this. Now, what if it's less than 1? Like 1/2. Well, think about what that shape is. That still goes up, but it goes up with a different curvature, right? If the exponent is less than 1, then instead of going up, it's going to go more out. So do we have any of those? Well, picture D describes that. Is there an equation that has an exponent less than 1 and a positive coefficient? Because that would be in quadrant 1. Is there one? 39? Is its exponent less than 1? Is its coefficient positive?
Yes.
So its shape is going to be out. Now, if it had a shape like this, tell me about that. That would have an exponent less than 1, but a negative coefficient. That would be picture E. Are there any E's? Now 40 is not, because 40 has an exponent bigger than 1. So 40 is more this shape right here. This is 40, because its exponent's bigger than 1. This is an exponent bigger than 1. This is an exponent less than 1. Now what about a negative exponent? What do negative exponents look like? What does that look like right here? What's that look like? What kind of curvature does it have? This? So do we have any of those? Negative exponents. Number 41. What graph does 41 match up with? I'll give you a hint. It's either A or H. It's H. Why is it H? Because it's negative. It's down below. Anything else? What about 38? Has a negative exponent. What's it match up to? It's either A or H. A, because it has a positive coefficient. And those are the only negative exponents. So, 37, powers bigger than 1, coefficient's negative. It's going to look like this. 37 is going to look like this. If your power is bigger than 1, in a power function, if your power is bigger than 1, you have a shape like this. Some variation of that. If it's less than 1, you have some variation of that. And if it's negative, you have some variation of this. These are the ones with positive coefficients. Negative coefficients, same thing. Power bigger than 1, power less than 1, power negative. So if I gave you an equation like this and said match it to one of those graphs, which graph, A through H, would that equation go with? It's a negative exponent, positive coefficient. Which one would it go with? A. Very good. Let me give you one more. Less than 1, negative. Which is that going to go with? Which letter? This tells me I'm looking in quadrant 4. What shape is that? Which one? H, G, F, or E? E. It's E. This is the shape when your power is less than 1. This is the shape when your power is less than 1. Positive, negative, coefficient. These are not power functions. I thought I had written a couple that weren't, but maybe I erased them. This is not a power function, even though it's to a power. It's not a power function because the variable is the power. In a power function, the exponent will be a number. X cubed, x to the 5th, x to the 4/3. Those are power functions. These are called exponentials, and they have a different shape and different rules. You know that already. Okay, one more thing on this section to talk about, and then we'll be done with this section, and that is problem 17, I guess down to 26 or so. Talks about variation. Direct variation and inverse variation. Do you remember the difference between those two? Direct variation and inverse variation. Do you remember the difference? You've heard those words before. So let me give you an example of one, see if you can figure out which one it is. I go to the store, or no, let's say John and I go to the store, and we're both gonna buy bananas. And bananas are 50 cents a pound. I buy 3 pounds, he buys 4 pounds. Who pays more? This is not a hard question. He does. Why does he pay more? He bought more. That's called direct variation. If you buy more, you pay more. If you buy less, you pay less. That is direct variation. When both variables, how many pounds you buy, how much it costs, if they both move in the same direction, both either get bigger together or smaller together, that's called direct variation. The formula for direct variation is y equals kx. Or you might think of it as y equals mx, because it's a linear relationship. This is called the constant of variation. It's the same as the slope. So in my banana problem, if this is the cost and this is the number of pounds, then C would equal 0.50p, right? 1 pound of bananas cost me 50 cents. 2 pounds cost me $1, and so on and so on and so on. That is direct variation. Okay? Now, Thomas and I live right next door to each other. Not in reality, but let's just say for a moment we do. We live right next door. He wishes we lived right next door. We live right next door to each other. We both leave for school at exactly the same moment. Okay? I drive 30 miles an hour. He drives 50 miles an hour. What happens? He gets to school before I do. So in other words, as his speed went up, his time went down. As the speed went up, the time went down. That is not direct variation, because remember, in direct variation, they both go up or they both come down. That's an example of inverse variation. And the formula for inverse variation is y equals k over x. Inverse variation is where you got your two quantities, but instead of moving in the same direction, they are moving opposite each other. So one's going up and the other one's going down. Think in chemistry class. What happened if you had a gas? What happened to the volume of the gas as you increase the pressure? As you increase the pressure, the volume decreases. Another inverse variation. And K is still called the constant of variation. By the way, this right here could be written like this, and it's okay to write it that way. We don't usually, but it's okay. This is rate times time equals distance. Remember my example about rate and time being inversely related? You know that already. That's your formula. So when you read a problem, and I'm about out of time, but number 17 says, the area of a triangle varies directly as the square of the length of its size. Directly means I'm going to use this formula, and I'm going to say the area varies directly as the square of the size. So instead of y varying directly as x, its area varies directly as s squared. That's the problem. I didn't make that up. That's what the problem says. And this would be the way you would set it up. Okay? Now, I see we're all packing up. We have 2 more minutes, and I want to make sure we're clear on this. If I said to you, give me a real quick sketch of y equals 1/3 x to the 5th. what shape would you draw on your paper? And I only want one quadrant, so you're gonna draw here or here. What would that look like? It's positive, this, so it's gonna go something like this? And then one more, what about this? Now, first of all, it's got a negative coefficient, so it would be in quadrant 4. And the exponent is negative. So it has the shape of the reciprocal function in quadrant 4. All right, do I see you tomorrow? I do, don't I? Didn't you decide to do?
Yes.
So we know we have a quiz tomorrow?
Yeah, Friday hugs too.
And tomorrow, Friday hugs, yep. Yep. We'll need to hug after we take the quiz, probably.
Nah.
But you